All right, gang, Math 6610, going to dive into dependent samples t-test. I think it's one of the most straightforward, at least in terms of calculations. And again, keep in mind that my perspective in teaching this content at a graduate level course is to review and make a connection between how I want you to report the results once you get into my 6996, 6997, and 6998 sequence. But I think the difference, or at least I don't know, probably the main challenge with that I see with dependent samples t-test certainly are not the calculations, but understanding the difference of when dependent samples t-test and independent samples t-test are actually needed. I can't stand that. Okay. So a dependent samples t-test, sometimes called a matched pairs t-test, violates the independence assumption because the measurements are taken on the same subjects or the same people. You can't violate the independence assumption any more than taking measures on the same person. Now we'll get into other aspects of that with like repeated measures, ANOVA repeated measures, where we take more than two measurements. And then we'll get into some mixed models where we also violate the independence assumption because of the nested design, not necessarily because the measurements are taken on the same person at multiple time points. So just to give you an indication what happens with an independent samples t-test, population 1 and population 2 are independent. Now, if you think about it in the context of the dependent samples t-test, population 1 could be a pre-test, and population 2 could be a post-test. Now, if these subjects are randomly selected from a population, possibly school district A, and then there's a post-test given at school district B, well, there's reason, even though you're doing a pre-test, post-test design, which, by the way, would be a very, very wacky way to design the experiment. But what I'm trying to give you is the context of an independent samples t-test where you have a pre-test and a post-test. Again, poorly designed experiment study, but again, if this group was randomly selected from one school district and this for another school district, and there's no intersection leading us to believe these are independent, then we carry out as the study as we would as I demonstrated in the previous video. That's not what we're doing here. We are, our population 1 and population 2 scores are taken on the same individuals. So student number 1 takes, for example, a pre-test. Sometime later they take a post-test. Typically there's some sort of intervention in here, so we want to kind of tap into the effect of the intervention. We have a second student who has a measure here and a measure here and so on and so forth. So we usually have N cases. So our focus is on the distribution of the differences, as I'll demonstrate here in just a second. Now, so we create a new variable in problems like this, where we have measure 2 minus measure 1 and measure 2 minus measure 1 for each of the subjects in the study. The test statistic turns out to be the mean of these differences. See where I've titled and labeled this variable D. So we take the mean of these minus the mu sub 0, which is hypothesized in the null hypothesis. This is typically 0. And then divided by the standard error. The standard error turns out to be the standard deviation of these measures divided by the square root of n. We have a slight adjustment to the effect size only because this is the effect size that is required to calculate the Priory power. I don't like Cohen's DZ for reasons I'm not going to go into. I don't think I'd ever report it in literature, but because the Cohen's DZ is used to calculate the power analysis, not Cohen's d, not to be confused with it. Again, Cohen's dz. And here's the formula, very, very, very straightforward. The only thing, we have the variance of sample 1, variance of sample 2. That would be like the pretest, the variance of the pretest, and the variance of the post-test. This would be the mean of the pretest, the mean of the post-test. So this is the way you calculate, even though our test statistic doesn't use these measures directly. One caveat, the R is just a straightforward correlation between measure 1 and measure 2. So that's very, very simple to calculate. The 95% confidence interval stays in the same form, your estimate plus or minus the t-critical from the distribution that we know that we have to use. In this case, it's the t-distribution times the standard error. Now, I want to bring in a data set. So let me bring in pretest. So let me just drag it there. See if I can get that, and then add. This is always challenging, and I really don't understand why it's challenging, why it puts 2 of those there. And not only challenging, extremely annoying. Well, shoot. All right. And then let's just attach our data. And let's look at the head of the data. So we can see that what we have now is we have the pretest and the post-test. So what I want to do is I want to create a new variable called the difference, and this is going to be the post-test minus the pretest. Now, I kind of like at this point, when I create a new variable, I like to create a new data set, a new data frame. So I'm just going to do that. So new data, I'm going to create a new data frame with subject, pretest, post-test, and the difference. I'm going to attach that so I can conduct the analyses. And now you can see that if I type in new data, you can see that we have not only the pretest and the post-test, but this new variable difference, which is important to, well, it's critical to the calculations. All right? Make this a little larger. So what we have is subject number 1 improved 12 points. We can see that we have a couple of students who decreased. One went from 88 to 85, and so on. Yeah, that just happens for one reason or the other. Now, the next thing I would want to do is come in and do the calculations. So I would now want to do the mean of the difference. Again, notice how my attention changes from pretest and post-test to the difference in the two. And that's the nature of the dependent samples t-test. So I have a mean difference of 5.9, and I have a standard deviation of 5.61. Again, notice that my calculations are on the new variable difference and not pretest, post-test, although pretest and post-test were clearly used to create the difference. All right, so moving into the test statistic, this should all be pretty clear. Sample size 10, so the test statistic is 3.328. So I need a distribution with degrees of freedom n-1, since n is 10, degrees of freedom 9, so I need the area in these curve in the tail. So it's probably going to be easiest just to find this area because the PT function finds area below, and I just have to type 1 minus, not a major deal, but whatever. So PT, so negative 3.328. Degrees of freedom 9, and of course I have to multiply that by 2 because I have 2 areas of rejection. So I get a p-value of 0.008, which would be reported as p less than 0.01 for reasons that I have described previously. In terms of the confidence interval, The confidence interval here will be, again, our test statistic, our estimate, I'm sorry, and our T critical. So that should be pretty obvious by now that we have QT, 2.025. In the left tail, degrees of freedom 9. So negative plus or minus 2.262 in standard error as defined previously. So works out to be this. Now, what will happen is these results will be completely opposite, meaning that the p-value will be the same, but I'll go ahead and tell you that the 95% confidence interval will run from negative 9.91 to negative 1.89. The reason being, I calculated the post minus the pre to get difference. R, by default, will take the first score minus the second score, so it'll be pre minus post. So you're going to have some things that'll be flipped. Namely, all these differences will be flipped. This will be minus 12, minus 6. This will be a plus 2, and so on. All right, now let's dive into the write-up for a dependent samples t-test, and I'll show you how we find this stuff.